Hello everyone, I hope this video finds you well. When I assigned this problem from 1988, I honestly looked at it and thought it was straightforward. And when one of you came to office hours, I realized that perhaps it's not as straightforward as I had thought. So let's go ahead and give you a solution that you can work with for this problem. I'm going to assume you've already read the problem. There's a circuit with a switch open, and if that switch were closed, the 3 microfarad capacitor would be connected, but it is not at the moment. And we do have a circuit that exists then, which is essentially just this, because that open switch eliminates that leg on the right. So we have a circuit. And it's not immediately obvious what's going on in terms of what's in series and what's in parallel. So let's look at that a little closer. Again, we tend to think of positive charge flowing, even though in reality the opposite is true. So labeling the terminals of the battery positive and negative, let's follow the charge. All of the charge that leaves the battery goes through the 6 ohm resistor. At this point, it reaches a junction, and it can go through the 4 ohm resistor back home, so to speak, or it can go through the 2 ohm resistor, at which point it will reach this junction. Now, no charge will go here because this is an open switch, but charge that goes through the 2 ohm resistor will indeed go through the 10 ohm resistor and then back home. So what we really have is one resistor that is in series with a parallel connection. But within that parallel connection, we have a 4 ohm resistor and then a 2 and a 10, which are in series with each other. So these two are in series, then they together are in parallel with the 4 ohm, and together that network is in series with the 6 ohm. I'm going to redraw it. Now you might say we could even draw a simpler diagram, another redraw. And this redraw, in a way, is helpful as well. Now, of course, this is my 6 ohm resistor. This is my 4 ohm resistor. But I've replaced the 2 and the 10 with 1. What would that value be? Of course, 12, because those two are in series and they add up 10 plus 2. Okay, so now I can begin to find the equivalent resistance of the circuit. For the parallel portion, 1 over R parallel equals 1 over 4 plus 1 over 12. Again, I'm sort of working off of this drawing in my mind. I found that R parallel, that these two in parallel, are equivalent to a 3. They are then in series with a 6, so the total resistance of the circuit is 9. The current flowing in the battery is just Ohm's law solved for I, and we have 72 volts divided by the total resistance of 9. So we have 8 amps. In part B, we're asked to find the current in the 10 ohm resistor. This is the 10 ohm resistor. And I think kids might be inclined to think of it just as a 10 ohm resistor, but of course it's in series with a 2, and so the 10 ohm behaves as far as the current is concerned like it's a 12 ohm resistor. So we're gonna use that thought later. Don't forget that the current in any location is the voltage across that element, that resistor, divided by the resistance that is important. So I think we need to find the voltage dropped across the parallel. What if I put a voltmeter here, or for that matter, a voltmeter here, because of course a voltmeter here would measure the same number as a voltmeter here because they're elements in parallel, resistors in parallel. What is the voltage across the parallel portion? And that, of course, is just the total current, some of which is here and some of which is there, but the total current goes through the parallel portions. So it's the total current times the resistance of the parallel portion. So we know that the voltage across the parallel portion is 24 volts. And again, when you're looking for the current in the 10 ohm resistor, you might think that you're going to put that voltage that we just found, 24, over 10, because indeed it's a 10 ohm resistor. But again, it's in series with a 2, and it's really, when the electrons arrive, they don't see a 2 and a 10, they just see a 12, because that entire segment has a resistance of 12. And so there's 2 amps in the 10 ohm resistor. What's the potential difference across the 10 ohm resistor? We know the current that flows through the 10 ohm resistor. And we also know that that leg behaves as if it's got a 12 ohm resistance. But I only want the voltage across this segment here. So I know that the current is 2 in that location. I'm looking for the voltage across the 10. And of course, I'm going to use my unifying equation, V equals IR. It's critical that we realize that the current that matters is the 2 amps that is in that parallel leg that contains the 10 ohm resistor. And I'm going to use the 10 ohm resistance. Now, if I'd used 12, I would have gotten 24, and I know the total voltage here is 24, but I want the individual voltages. The product of 10 and 2 is, of course, 20. And I'm just going to double check here before I put a box around it and see, is the voltage drop across the 2 ohm resistor the other 4 volts that will make it sum to 24? And it checks out. 20 and 4 do add up to 24. Now, I think that actually is the most challenging segment of the problem. But I will quickly finish the problem. Now the switch is closed and the capacitor is going to be part of the circuit. And of course, after some time, the currents reach constant values. And then at that moment, the capacitor is charged. We're asked to find the charge on the capacitor. Now, this just goes back to the definition of capacitance. Capacitance is Q, the amount of charge per volt. And solved for Q, we get CV, the capacitance times the voltage across the capacitor. We just need to put in the correct values for capacitance and voltage. Now, of course, the capacitance is given. It's 3 microfarads. And the voltage across the capacitor, again, I want to emphasize, because it is now in parallel with these elements, it shares the same voltage that is across here and here. So as we've seen before, that's 24 volts. And so we have 72 microcoulombs, or if you choose to put in the exponent power of 10, you would have reached 7.2 times 10 to the minus 5 coulombs. Last, we're asked to find the energy stored in the capacitor. As we talked about in chapter 19, energy for a capacitor is 1/2 the charge stored times the voltage across, or 1/2 CV squared. Either one gets you where you want to go. I tend to think, because I'm confident of this number, I'm going to use this because it's just a little quicker. Given an answer of 8.64 times 10 to the minus 4, of course, energy is measured in joules. And there we have it. I'll see you in class.